So there are three states of matter. We have the gas state, the liquid state, and the solid state. Okay? If we consider what is a gas, if you think about it, okay, gas is simply particles that have separated away from one another. So in this room is filled with gas. All kinds of gases, oxygen, and carbon dioxide, and nitrogen, okay? And those gases they're so spread apart that we don't really see them because they've spread themselves apart from one another, okay? However, when you move from the gas phase into the liquid phase, okay, those particles start to come together. They come close together. They attract to one another. And now, instead of being far apart, they're touching. And they're rolling, basically, they roll over each other. They're rolling. And that's why it's in the liquid phase, because the particles are simply just rolling over one another. But they're touching. All right? And then you move from a liquid phase to a solid phase. And that's when they stop rolling and they become fixed. They get stuck in one position. And that's where they're staying. They're staying in that one position. Okay? So they've lost the momentum, in other words, to roll over each other, and now they're just stuck in one place. And they have become a solid. So every piece of matter can go through these phases. They can all go through it. So often, if somebody asks you about oxygen, you think of it as in the gas phase, because that's the phase that you know of it to be in. But can oxygen be in the liquid phase? Yes. We can condense oxygen so that it is a liquid. Albeit it has to be very, very cold to get it in the liquid phase. But you can do that. You can make it in the liquid phase. And even a solid phase if you could get it cold enough. Okay? You could put it in the solid phase. So all matter can go through these changes. The one that we know, or the best example that we could probably think of is water. Right? Ice to liquid water to vapor, water vapor, gas. Okay? Because we see those phases all the time with water. But water isn't the only thing that does that. Everything can do that. It just depends on how cold you can make it or how warm you can make it to cause it to go through those. Lots of metals. Metals are solids at room temperature, but if you heat them up hot enough, they're going to melt, right? They're going to melt, and then if you could heat it up even more than that enough, it would vaporize. Okay? All right. So here we see ice, liquid water, and water vapor, gas, the three states of water, of matter. Okay? And everything can go through those states. So, can't see that very well, but this is essentially saying the solids are closely packed together, whereas in a liquid, they're not as closely packed, they're rolling over each other, and as in a gas phase, they're bouncing around. Okay? They're bouncing off the walls, they're bouncing off each other, they're just going all over the place randomly. Okay, well, not so random if you consider it like a pool ball that you shoot at something and it bounces, its trajectory will change according to its initial trajectory, but that's what they're doing. Okay, so matter is essentially everything around us, and it can go through those phases, and it consists of atoms. Everything around us is made of atoms, and everything around us is matter. So what are the physical properties of these matters, of this matter? Well, physical properties are things that we observe without changing the composition or identity of a substance. Meaning, if I am talking about the physical properties of water, okay, H2O, a physical property of it is that it freezes at 0 degrees Celsius. And it boils at 100 degrees Celsius. So when water freezes, is it still water? Yes. It has not changed chemically. It has only changed physically. When water boils, is it still water? Yes. It has not changed chemically. It is still H2O, whether it is solid, liquid, or gas. So these are physical properties of it, because they don't change the chemical composition of it. They change only the physical state. Okay? So that's what we're talking about when we're talking about physical properties. If it doesn't change chemically, it must be a physical property. So what do you think it is if it changes chemically? A chemical property, a chemical change. Okay? So a chemical change would be something like H2 plus O2 forming H2O, right? Hydrogen and oxygen change chemically to form water. That is a chemical change. Okay? This is chemical, this is physical. Okay? H2O solid to H2O liquid. That would be a physical change. This would be a chemical change. Chemical changes are observed through chemical reactions. That's how I can observe that a chemical change is occurring, because a reaction is taking place. Okay? Okay, so here's some more physical ways, properties. So iron is magnetic, right? I want to separate iron from sand. You guys kind of looked at this in the lab the other day, if you did this lab, where you took the magnet and you moved it over the iron, right? And it became, you could separate the iron from the sand, because the sand is non-magnetic and the iron is magnetic. Okay? And that would be a separation by physical properties. So you can separate things if they are not combined chemically by physical means. So if I want to separate salt from water, so I dissolve salt into water, they have not combined chemically. They are simply a mixture of water and salt, right? I have dissolved the salt into the water. So I can separate them physically, by physical means. And water boils them at a much lower temperature than does a salt. So if I boil the water away from the salt, what's left over? The salt. And I have separated them through physical means by doing that. Okay? That is a physical separation, just like this is a physical separation. They are not combined chemically, so I can separate them through physical means, like magnetism. Okay? Okay, we talked about chemical properties. Chemical properties we observe through chemical reactions. Chemical reactions are a process of rearranging, removing, replacing, or adding atoms to products to make new substances. Hydrogen plus oxygen, water. It's something new. Okay? Whenever you create something new, a chemical reaction has occurred. Okay, so classify the following as either a chemical or physical property. Color. Physical, good. That's a physical property. Flammability. Good. If it combusts, what does that mean it's reacting with? That's right. It's going to become, so if I burn wood, then now it has become something new, right? It's no longer a piece of wood, it's a piece of carbon. Because all the oxygens and hydrogens on that wood have been burned off of it. Okay, they reacted with the oxygen in the air, and now I'm left with carbon because it was an organic piece of material, right? All right. So flammability is reacting with the oxygen in the air. It's reacting with oxygen, and that's why it's flammable. Hardness, how hard it is. That's physical. Odor. Okay, so let me ask you this question. If I smell something, does it change that thing chemically? Okay, so is it a physical property of it or a chemical property? Okay, it's physical. Okay, it is a physical property because it has not itself. If I smell sugar, I didn't change the sugar. My brain understands that to be sugar because the chemical it is sends a signal to my brain saying that smells good. Okay, and that's why we all have cravings for sugar because we have to have sugar in our bodies, right? To undergo, to create energy. So taste, same thing, right? Taste, same thing. Because after your enzymes go and break up the food, they've changed it chemically, but it doesn't taste the same anymore. It's that initial taste that you're getting from that chemical. Your brain, the receptors on your tongue are binding it and understanding it to be something because of the shape it has, the structure it has, and your brain perceives it.
For example, if you have something and you change chemically, sometimes you can change the taste too.
Absolutely. So what happens when you let your milk sit out?
Oh, gross.
Does it taste good?
No.
No, it tastes. So milk souring. Oh, wow, I said that word terribly. What type of change is that? That's a chemical change because you have taken the proteins and the things in the milk and you have changed them chemically.
So the taste will be chemical change?
For which?
For that, for the milk.
The milk got soured. That's a chemical change. The taste, how the milk tastes, is a physical. It's physical property. Okay, because it tastes the way it does because it was already changed. Okay. Okay. Classify the following as either a chemical or physical change. Water becomes steam. Physical change. Butter turns rancid. That's kind of like the milk example. That's a chemical change. Wood burning. Snow melting. Leaves decaying. Whoops. Okay, so D is in fact a physical change. E would be a chemical change. The leaves decaying. Because the bacteria that are breaking down the organic material in that leaf, they're changing it chemically. Okay, they're decaying it. Okay, I'm sorry. It's a chemical change. Two more vocabulary. Intensive properties and extensive properties. Okay? An intensive property is a property of matter that is, this is what you need to remember, independent. Intensive is independent of the amount of matter. It is not relying on how much you have. So an intensive property does not change whether you have a lot or a little of that substance. Okay? And that is contrast to an extensive property, which is a property that is dependent on the amount of matter that you have. Okay? So, intensive, independent. Extensive, dependent. So here they give examples. Okay, don't worry about specific gravity. That's not something you guys really need to learn. Density, though, that's a great example. Because the density of a substance does not change, whether I have a lot of it or just a little bit of it. So if I have a piece of wood and I measure the density of that wood, and then I cut it a little piece off of that wood, and I measure the density of that little piece, the density of both of those will be exactly the same. They will not change, whether I have a lot or a little. So that is why density is independent of the amount I have. It is independent. Because the amount I change the matter by, I change the mass by also. And density is a measure of the amount per milliliter, the mass per milliliter. Okay? So, in other words, here's my piece of wood. Okay? Let's say the density is equal to 0.79 grams per milliliter. Okay? I cut a little piece off. I have changed the volume and the mass, right? So that little piece will still have a density of 0.79 grams per milliliter because the volume and the mass have both changed and decreased. So they will be the same ratio, grams per milliliter ratio. Okay? The density does not change with the amount. So this is an intensive property. Okay? Nope. No, but that's a really good example. Okay? Other examples are, we'll get into it, concentrations of solutions and things, but.
Okay, so when you talk about density of the glue, is the way it's compacted together?
How close the molecules are to one another. Okay, and how heavy each molecule is. So that's what we're talking about when we're talking about density. A piece of iron, the iron molecules are close together in that solid state, and therefore they have a high density. Okay? But a piece of wood, those organic molecules aren't packed super tight together. They're spread out. They have room between them, and so therefore their density is less than a piece of iron where the molecules are closely packed together. That's why the mass of a piece of iron, so let's say you had 1 milliliter of iron versus 1 milliliter of wood. Okay? It's the same volume and the same space, right? But this one would weigh a lot more because the molecules are much closer together than in the wood. They're farther spread apart. Okay?
So then what you were saying is if this has to be cut into half, or let's say 1/3 of it, you're saying that the density would stay the same, but the mass and the volume would change.
And that's why the density stays the same. So, for example, let's say I have something that is 10 grams for every 5 milliliters. Okay? Then what is my density? 2 grams per milliliter, right? Does everybody agree?
Yeah.
Okay? Now, if I cut that thing in half, then it is 5 grams for 2.5 milliliters. What is my density now? 2. So did the density change when I cut it in half? No, because I cut the volume and the mass both in half, right? so the density did not change. So this is an intensive property. It doesn't matter how much of I have. If I have a whole bucket of water versus just a cup of it, the water will have the exact same density whether it's in a cup or a bucket. Okay? So that's... I'm sorry? Density changes with temperature. Yeah, so you have to specify the temperature at which you're measuring the density, okay, of something. That's right. Any other questions? Yes. 25 degrees Celsius. That's what they consider room temperature. Okay, whether your room's really at 25 degrees Celsius or not. Okay, a lot of people think that's a little cold, but so, but yeah, that's what it is. About 37 degrees Fahrenheit.
Is room temperature.
Room temperature. No, I'm sorry, I was wrong again. Oh no, that's 98.6 degrees Fahrenheit. It's 37 degrees Celsius. Excuse me. Gosh, no, I can't think in Fahrenheit. I'll have to think about that. Okay. All right, so that's what we're talking about when we're talking about these intensive properties. Okay? The color of your shirt. Is that intensive or extensive? Intensive. Okay? It's an intensive property. It doesn't matter how much of the matter I have, it's going to be that color. Okay? The boiling point of water. The longer it takes to boil, but the boiling temperature, it's intensive. Because the temperature at which it boils is 100 degrees Celsius, whether I have a little bit or a lot. And you're exactly right, Jessica. It's going to take longer for that bucket to reach 100 degrees Celsius, but once it does, it will boil. And the cup reached 100 degrees Celsius sooner, but it was still 100 degrees Celsius when it boiled. Okay? So it's intensive, right? That's an intensive property. It will boil at 100 degrees Celsius if it's water. Okay? It doesn't matter how much of it I have. Okay? Okay, I have some white pages. Okay. Classification of matter. So, matter is classified into two categories. It is either a pure substance or a mixture. Okay? And a pure substance is a substance that has only one component. Now, that is not to say that it is just an element. Okay? A mixture is a combination of two or more pure substances. So I take pure things, I put them together, and now it's a mixture. The air that we're breathing right now, there are more than just one element in the air. There's nitrogen, there's oxygen, there's carbon dioxide, there's even trace amounts of hydrogen, okay? So it's all those pure elements, and they're all mixed together, right? And that's what creates our atmosphere. There's even probably water vapor, especially if you live in San Antonio. The humidity is crazy, right? Oh, Houston's worse. Okay, so, but that's all mixed into the air, right? And it's a mixture of all those components. So, a pure substance can either be an element or a compound. So here's some elements. And remember, elements a lot of times don't exist as just single things. They have to be diatomic. Hydrogen does not just exist on its own as just a single hydrogen. You have to have two of them. So it's H2, and it's O2, and it's N2. Okay? Those are the gases, oxygen, nitrogen, and hydrogen. What's that? Okay? So here we have some elements. They are pure substances. In the air, they're not pure, right? Because they're all mixed together. So they're not pure. But if I create oxygen and I isolate it, I can have an isolation of pure oxygen. Okay? So how would I classify this? Do I classify it as a pure substance?
No.
Okay, so is this an element or a compound? It's a compound. Okay? It is a combination of hydrogen and oxygen. But it is a pure thing if I have it in a pure form. I can have pure water, right? I can make water pure and it would be a pure substance. Okay, I want to make that point because that's often a point of confusion for people. This would not be classified as a mixture, but it would be classified as pure water. Okay, so compounds are pure substances. Compounds are pure substances. All of them are. Here's another one. Table salt. There you go. That's right. Because it's two pure things, right? So here we have table salt, sodium chloride. It is a combination of sodium and chlorine in a compound, but it can be a pure substance. I can have pure sodium chloride. Okay? Now, if I take H2O plus NaCl and I mix them together, they form salt water. That is a mixture, right? Because when I put those two things together, do they change the water or the salt chemically? Do they react? No, it is not a chemical reaction. It is not a chemical reaction. That means if I want to separate the salt from the water later by physical means like boiling away the water, I can do that, right? I can boil away the water and I'm left with salt. So this is a mixture. So mixtures are combining pure substances and putting them together. H2O plus carbon dioxide. What do we call that? This is gas. This is a liquid. Two pure substances, I put them together. Get soda water. Right? You know all that bubbly stuff in your throat? That's what it is. That carbon dioxide that you put into the water. You mix it into the water, right? It becomes a mixture of water and carbon dioxide. What's that? You just like the syrupy taste of it? No carbon dioxide? You're unique in that. Most people once their soda goes flat, they're like, I can't even drink this, and they throw it away. Then they're like, this is way too sweet. I can't drink. It's too sweet now. I can't drink it. Yeah. Yes.
Okay, so what you're saying is, for our mixture, you have to have two fuel substances.
That's right.
Only two fuel substances can give you a mixture.
That's right. As long as they're not reacting. So this is not a chemical reaction. I'm not reacting those to create something new, right?
No.
They will separate later, right? I know that if I open my soda bottle, what happens to all that carbon dioxide? It escapes. It can separate itself, right, from the water. And it will do that. So it's a mixture in the bottle. I open the bottle, and now the carbon dioxide is escaping. What's that? Yeah. The bubbles are coming up. They're going out. They say, I don't want to be in here anymore.
Only 2 or 2 or 4?
It could be more than 2. It could be any amount of things. Okay? There is no limit to how many things you can have mixed together. As long as they are not reacting chemically, that is considered a mixture. Yes?
You know how you said a compound or an element can be a super substance, like NaCl or H2O. Could it be like 3 things that are pure? Maybe still be three things?
3 elements? Sure. Yeah, I could have something like magnesium phosphate, right? That's a pure substance. I could have pure magnesium phosphate. Or I could have pure glucose. Okay? And somebody showed me this as a license plate earlier. Somebody had that on their license plate. Sugar. That's sucrose. This is glucose, sucrose. Okay? But yeah, that's a pure substance. Pure sugar is a pure substance. Okay? So it doesn't matter how many of each thing you have in the compound, it's pure. Okay? But if I take water and I mix it with sucrose, sugar in our cupboard, then I get a sugary water solution. Okay? Sugar water. You sure can. You boil it away, it will boil away. Okay, but you gotta be careful about that. It will boil away because the boiling point of water would be lower than sugar to boil the water away. But yes, you can't, because they have not combined chemically. They have only combined physically. Okay? So they can separate. Now, with a mixture, there's 2 types. There are things that we consider homogeneous mixtures and other things that we consider heterogeneous mixture. Okay? The root of the name homo means the same. So homogeneous means the same throughout. So if I have a beaker of salt water, okay, I take a sample of the salt water right here. And then I take another sample right here. Is there any difference in the amount of salt right here as there is right here? Salt has been dissolved into this. Is there any difference? The answer to that is no. There's no difference. Okay? There is the same amount of salt right here as there is right here. So we would consider this to be homogeneous. Okay? It is a homogeneous solution. It is the same throughout the entire solution. Okay. Now, if I take, let's say, 2 solid substances. Let's take some twigs and some dirt. And I mix those things together. Is that a homogeneous mixture? No, because I don't have a perfect separation. I haven't separated the particles perfectly throughout the entire solution. I could take a sample at one part of it and a sample at another part, and they wouldn't have the same composition. I might have more wood at one part than I do at another part. Or the dirt's falling through the wood, and so it's collecting at the bottom. It's not homogeneous. That would be a heterogeneous solution. Okay? So the best way that I can explain to you how you can identify homogeneous versus heterogeneous. Yes, solid be heterogeneous. Perfect. Okay. Is if I have to do the mixing, it's not going to be perfect. It's not going to be homogeneous. So if I'm trying to mix my salad, there's not going to be a perfect distribution of my cherry tomatoes in there. Okay? It's not going to happen. So it is heterogeneous. Doesn't matter how long I mix it. It's going to be heterogeneous. Okay? But if I take sugar and I let it sit in water, it will dissolve. Do I have to do anything to allow it to dissolve? I could mix it, but do I have to? Could I let it sit there overnight and it would dissolve on its own? Yeah. So I don't have to do anything, right? The particles will separate themselves into the solution. So because they separate themselves, they do a perfect job. They do it perfectly. And that is a heterogeneous solution. It is heterogeneous. Yes.
Like a cake, I was making a cake, you know, like it gives me a specific amount to put like eggs or whatever. If I'm making it, but it's the same, so I don't think so. I mean, it's the same, you know. So
Okay, so that it's not exactly a homogeneous solution because you can't ensure because the particles aren't separating themselves, so you can't ensure that every single piece of that has the exact same composition throughout. Okay, perfectly. All right. So it would be more considered a heterogeneous solution because there might be slight, even though they're little, there might be slight differences throughout the entire system. But if the particles separate themselves by themselves, they will do it perfectly. Okay, and that would be homogeneous. All right. So here we see a pure substance, water. Something got dissolved into the water. This is homogeneous. But I don't know if you can see that rock very well, but that rock would be considered a heterogeneous mixture because if you look at it, there's differences throughout it. So you can see here, it's not mixed perfectly, right? So this is a heterogeneous mixture of minerals in the rock. They're not the same. The composition is not the same throughout the entire thing. So that would be heterogeneous. Okay, now here comes the real fun. Significant figures. Okay? Yeah, go ahead.
Let's go back please with Andrew and Homo. Okay. So how much is that explanation on chapter 1? One night.
Homogeneous. So that would be homogeneous because it separates itself. Okay? So here's some examples. Okay? Air. The air in this room, it's a mixture of gases, but those gases have separated themselves perfectly throughout. Okay? They will distribute themselves. So if I take a sample over here of the air and a sample over there of the air, it will be the same. So it's homogeneous. Salt dissolving in water does it itself. Oil in water, obviously it's not going to mix at all. I don't even want that terrible example. Okay, they don't even mix, but whatever. Okay, salt and pepper, right? I could try to mix that salt and pepper really well, and it looks like it's a pretty good mixture, but it doesn't separate itself. It is not a homogeneous mixture because there could be differences between pepper versus salt particles at one part and another part. Okay? So it's not a heterogeneous mixture. Not.